A flop is any instance where a computer adds, subtracts, multiplies, or divides. Okay? That is a flop. We're going to assume that computers can do this. I don't think you can take this class at MNU, but in other universities, you can take a class called Digital Logic Design. It would normally be inside like their computer engineering department. And you can even find a textbook if you're extremely interested. You can read a textbook about digital logic design, but we are going to avoid that topic altogether. What we really care is that computers can do this. And FLOP, by the way, stands for I'm trying to capitalize some of the letters, but I'm not very smart. Here we go. That's a capital L. Floating point operation. There we go. That's what I was trying to do. So an operation means add, subtract, multiply, and divide. Floating point means we're dealing with a specific data type. Floating point operation, FLOP. Exercise 2 says, consider the following function. Count how many flops are required to evaluate this function when we are given some real value for x. So we don't know what x is yet, but at some point in the future, a user is going to come up and say, x equals 5. And then you have to evaluate this function. How many flops are required? Just look at it, count how many times do you have to add, subtract, multiply, or divide to make this function work. Eight. Kevin, what do you say? 8. Becky?
I got 9.
9. Aaron? 7. Sage?
I'm not there yet.
Colin?
I think 7.
7. I think 5. Now, Connor, tell us why you think 8. Where do the 8 flops come in?
You multiply x times itself 3 times, and then you subtract and 2 more for the 5x, and then add and subtract x.
I want to change my answer, by the way. I'm going to say 6. It's going to be my answer. I said 5 earlier. I was wrong. So let me tell you my line of reasoning. And maybe I should type this out instead. Well, let me take this one step at a time. I'm getting too excited here. I'll just say step number 1. I'm going to calculate a variable that I'm going to call x squared. And I'm going to calculate that by multiplying x times x. Okay? And that's one flop. I know that there's 2 x's involved, but there's only one multiplication happening. And so this counts as one flop. Okay. The second flop is I'm going to save a variable or a value in my computer memory. And I can find out what x cubed is if I multiply x times the previous number I saved for x squared. Okay, so that's 2 flops. The third flop that I need is I got to find out what is 5x squared. And I can do that by multiplying 5 times x squared. The fourth flop is going to be subtracting. The fifth flop is going to be adding. And the sixth flop is going to be subtracting. So, I'm sure you all had the right idea. The most common answer that I would normally expect is someone to say, well, I need to multiply x times x times x. So that's 2 flops to get x cubed. And then x times x for x squared times 5. And that's 4 flops altogether. And then I've got to subtract, add, and subtract. So maybe the most common answer people come back and say is 7. But if you're thinking through it really carefully, you think, I could actually avoid having to do one of those flops as long as I use a previously calculated value for x squared to give me the x cubed part. And I mean, I know that's silly. It's like a little bit pedantic, but these are actually the kind of things that engineers think of. Because if you're about to build a data center and it's going to cost $100 billion, like I just saw a headline yesterday that said they were going to build a $100 billion data center in the Kansas City area. If you can reduce your compute requirement from 7 to 6, that means you can reduce the size of your data center from being 140 billion to 120 billion, you know, like think in relative terms. What percentage of the cost are we cutting because we're demanding less computer resources? Here's another one to think about. How many flops are required to evaluate this function given some natural number n? You have an answer?
Is it not 2?
2? Well, it depends on what n is. That's a hint for you. It's not going to be the same if n is 5 versus lowercase n is 10. You're probably overthinking it. Colin, do you have an idea?
N minus 1.
Yeah, n minus 1. And I hope you remember this from previous math classes, but the big sigma notation means I'm adding things together. So like g of 4 would be 1 plus 2 plus 3 plus 4. Notice there's 3 additions, and so the number of flops is n minus 1. So what if I want to evaluate this function at n equals 100? How many flops is it going to require? 99 flops. Very good. Now there's another moral lesson here that I'm going to preach at you for a second, which is imagine this picture. The area of this enclosed orange thing shape is what it would look like to add 1 plus 2 plus 3 plus 4 plus 5, right? Right? So if I was going to calculate g of 5, I could calculate 1 plus 2 plus 3 plus 4 plus 5. Or, it's the thought, what if I were to instead calculate the area of this square, this big old square? The area of this giant square is
Or area of the base. Sine squared.
what's the width across the bottom? 5. And what's the height?
5.
Yeah. This is a 5 by 5 square. And then now if I want to know what's the area of the staircase, in other words, what is g of 5? One thing I can do is start off by calculating half of this square, the triangle, slice it from like corner to corner. And then once I've sliced it from corner to corner and I've got like the triangular part, which is half the area of the square, it's 5 squared over 2, I need to add back these little bits that poke up above the triangle. And each little bit is shaped like a triangle. Do you know what the area of each little bit is? Yeah, each one of these little triangles has an area of 1/2. And how many of them are there? 5. So let me add back 5 halves. And the thing is, with this formula, to get the area of, the same thing, right? This is g of 5. With this formula, there was nothing special about having chosen 5, right? Like, I could have extended this to being 1 plus 2 plus 3 plus 4 plus 5 plus 6, and I've had 6 little columns. The tallest one would be 6 blocks tall, and then I could do the same problem. So g of n is equivalent to saying, let's take n squared plus n divided by 2. And the requirement to calculate n squared plus n is 1 multiplication, 1 addition, and 1 division. So that's 3 flops. So again, the moral lesson I'm trying to beat into you is that if you are really clever, sometimes you can design an algorithm that will reduce the number of flops that your computer has to churn out in order to make a calculation happen. And of course, this doesn't matter on my PC and it doesn't matter on your laptop because those are fast machines and we're asking very small problems. But out in the real world, there are big problems that even big machines struggle to keep up with. And where you can reduce the flop requirement on those big problems, that's going to mean you're saving time, you're saving money, you're saving the environment because you don't have to build another power plant and produce a lot of CO2 or whatever, I don't know. But efficiency is always better. And so in this class, in numerical analysis, we're primarily concerned with how do we get the best answer, the best approximation, while also using the least possible computer resources. And so we're always going to keep an eye out for the most clever algorithm for doing something. So that brings us to exercise 3, I guess. There's 2 reasons, and I already told them to you, right? If I ask you to give 2 reasons why we want to minimize the number of flops, time, money. my own advisor, whenever I was a master's student at Texas A&M, he was a guy that did computational fluid dynamics, which means he takes like a fluid dynamics problem, a geometry, a fluid type, what regime it's in, and applied it to his own computer simulation, which was basically his numerical solvers for a system of partial differential equations called the Navier-Stokes equations. And then he would write the C++ code to make it run on the supercomputer down at Texas A&M. And one of the things that he had to do after he had written his code and done all of his theory and he was ready to create his simulations is he would have to request time on the supercomputer, because there was a lot of professors and a lot of industries at A&M that wanted to use Texas A&M's supercomputer. And so they would give him some kind of allotment since he was a faculty member, and they would say, all right, your scheduled time to use the supercomputer is the 12 hours between midnight and noon on September 11th or something like that. And then you would have to wait patiently until September 11th came around, and then you have 12 hours where he could run his code on the supercomputer. And if his code took more than 12 hours to run, sorry, they were going to cut him off and let a different researcher use it, right? So time is important. The other thing is, like I said, money. If you can reduce the need for computers and you don't have to buy as many computers, if you don't have to run your computer as much, you can save money on electricity and so on. Exercise number 4. Count how many flops are required to evaluate this function at x equals 1.5 with 4 significant figures of precision. So we've got e to the x. And if I'm thinking about evaluating this function, my head is here. I think e to the x is an entire function. That means you can have a Maclaurin series for this function, and it has an infinite radius of convergence. It converges for the entire real line. And so if that's true, then the Maclaurin series is a completely valid way to evaluate this function on a computer, right? So we are going to evaluate this function by saying that this is the same as 1 plus x plus 1/2 x squared plus 1 over Shame on you guys. I'm just kidding. I know it's been a while. You took Calculus 2 at one point and you knew this. But the deal with the e to the x function is it's 1 over n factorial. Or if you want to use k, it's 1 over k factorial times x to the k. So 3 factorial is 6, because 3 times 2 times 1 is 6. 4 factorial is 24. 5 factorial is 120, so on. But every term in the Maclaurin series is 1 over k factorial times x raised to the k. And in theory, you do this forever and add up infinitely many terms. In practice, we are not going to wait around to add up infinitely many terms. We're only going to add a few of them. And if I want 4 significant figures of precision, then we can figure this out. Okay? We would say this is going to be the column that contains the terms of my Maclaurin series, and this is going to be the partial sums of my Maclaurin series. And so let's say this is x equals 1.5, and of course the terms are all going to look like 1 divided by k factorial. So maybe I need another column for my k's. And each term is going to look like 1 divided by k factorial times x raised to the power of k. And the partial sum is going to be the partial sum before it plus the new term. And what I would like is to get this number accurate to 4 significant figures. So I'm looking for 4.481 or 482. 4.482, we'll say. Unless it's 1/6, and then we'll call it good. We'll say 4.481 or 2. Okay, so the closest we get, the first time we get 4.481 is after this many terms. 9 terms? Yeah, 9 terms. And so the largest power of x we need is x to the 8th power. We're going to have 1 over 8 factorial times x to the 8th power. And how many flops do we need? Well, the first thing I would do is I'm going to calculate all of the powers of x. And I'm going to do them so that it builds up on itself, right? Every time I come up with a new power of x, I'm going to save that somewhere in memory so I don't have to repeat flops all over again. So to get up to x to the 8th, I'm actually going to need 7 flops. There's going to be 7 times where I have to multiply x times x to get, that's supposed to be 2 words, to get x squared x to the 8th power. Now, for the coefficients, I need to multiply the coefficient times x. It kind of depends on how you look at it, honestly, because there's 2 perspectives you could have. The first perspective is like, those constants are already known to us. We know what the coefficients of the series are. And so we'll just pretend like it doesn't cost any flops to come up with them. And then we only need flops to multiply each power of x times the coefficient, in which case there's only 7 flops, right? Like, because you got to do x to the 2 power, x to the 3 power, and then up so on up to x to the power. The other viewpoint is you could say, maybe we don't have those coefficients stored in memory, in which case you would need the 7 flops in order to multiply the powers of x, but you would also need, I don't know, another 7 flops just to calculate what those coefficients are, right? You would start off with 1 and you say, okay, divide by 2, divide by 3, divide by 4, divide by 5, divide by 6, divide by 7, divide by 8 to come up with the coefficients. And so you would write your algorithm depending on whether or not you wanted to store those in memory ahead of time or whether you were going to calculate them on the fly, in which case it would require another 7 flops. It depends on what your bottleneck is. Sometimes your constraint is you want to use less memory. Sometimes your constraint is you want to use fewer flops. But we're going to use 7 flops to multiply by the coefficients. And then lastly, we have to add things together. So 1, 2, 1, 2, 3. I think, is it going to be 7 again?
8.
You're right, it's going to be 8. 8 flops to add. So altogether we've got 22 flops. another way you can think about it is you get this with just one flop, and then every term after that you've got to have 3 more, because add, multiply, multiply. And so you've got 1 plus 7 times 3. I don't know. Every additional term you need in this Maclaurin series to get more accuracy, every term you add is going to be 3 more flops. Okay, consider the Maclaurin series of this function. It's the same one. It's still e to the x. Which term has the largest absolute value when x is equal to 2.5? And which term has the largest absolute value when x is equal to 300? So the first question, bullet point number 1, what term of this Maclaurin series has the largest absolute value when x is equal to 2.5? We can go back to my spreadsheet here. Look at the terms in column B and tell me which one of those terms has the largest absolute value. Yeah. The term where we have x squared, the x squared term of the Maclaurin series, has the largest absolute value. So this next question is a little bit tricky, but we can definitely figure this out. So each term looks like this. It's positive, and it's going to add x to the k power divided by k factorial. So make a ratio and this ratio is going to look like the nth term divided by the n minus 1th term. Okay, in other words, it's going to be x raised to the power n divided by n factorial divided by x raised to the power n minus 1 divided by n minus 1 factorial. And you know that dividing is the same thing as multiplying by the reciprocal, and so I can write x to the n over n factorial times n minus 1 factorial over x to the power n minus 1. What is x to the n divided by x raised to the power n minus 1? Here, I'll repeat the question. If I have here in the numerator x raised to the power n divided by this x raised to the power n minus 1, what is that? X to the 1 power. And then if I have n factorial in the denominator and n minus 1 factorial in the numerator, how does that simplify? Huh? I think Colin's right. This is just going to be n. Try it with a small example. Let's say n is equal to 5, then n minus 1 is equal to 4. And so 4 factorial would look like this. 5 factorial would look like this. So then you cancel out all the factors, and the only thing that remains is n in the denominator. So this ratio of the nth term divided by the previous term is equal to x divided by n. And in this case, for the second bullet point, we know that x is supposed to be 300. And so this ratio is going to be 300 divided by n. Now let's talk about why this ratio is important. Because every term is going to have the value of the term before it times this ratio equals that term. Let me write it for you here. I'm going to name this ratio R. This capital R means this ratio. And if that's true, then the nth term is going to be equal to this ratio that we just calculated times the n minus 1th term. So every term looks like the previous term times this ratio. And this ratio is 300 divided by n. If 300 divided by n is a number larger than 1, that means every term is larger than the term that came before it, right? And if this ratio 300 divided by n is less than 1, that means every term is less than the term that came before it, okay? And so we're going to start off having terms that are bigger and bigger and bigger and bigger and bigger, and then at some point they're going to become smaller and smaller and smaller and smaller and smaller. And when you get to that very, very, very peak, that peak is where this ratio goes from a number greater than 1 to being a number less than 1, where it goes from increasing to decreasing. So this is going to go from a number greater than 1 to a number less than 1 when n equals 300. If n is equal to 300, this is 300 over 300. So the 300th term is exactly the same as the 299th term. And they're larger than all the other terms that came before them, and they're smaller, no, and they're larger than the terms that will come after them. Those are the two biggest terms, is actually the 299th and 300th. They are the same value and they are the largest. And we can check this really quick, because it's always a good idea to check your work. And what I'm going to do is just extend this by 300. I'm going to look for a place where, oh, I guess that number is just too big. Yikes. So I think what happened here is that what it's doing, the way I wrote these formulas, is it's calculating a factorial of 17, which is not that big, but if you go on to like the factorial of 100, now that's a huge number. And the problem is you can't store the factorial of 100 in the double precision floating point data type, right? And so it's going to give me that number error. And then the same thing for x raised to the power whatever, that also becomes too large to store. And so at some point, whenever we try to do the factorial of 170, 171, it gets out of range. So what we should do instead is, I didn't even set x equal to 300 until now. But what we should do instead is we should say this is going to be equal to the previous term times 300 divided by n. And you'll notice we still get the same numbers when I type in that ratio. And so that way I'm not going to run into that problem where it gives me numbers that are too big to fit. See, that's the practical knowledge about knowing about your floating point data types. But in theory, this number and this number should be the same. The others are not the same. They just look like that because of the rounding. Let me see if I can fix the rounding so that we can actually see. Yeah, so 299 and 300 are the same term. Cool. Now, can we think of a scheme to minimize the number of flops it's going to take for large values of x? When I say large values of x, I mean like anything larger than 20, right? If I want to get a lot of accuracy without having to do a lot of terms, what should I do? Should I start with the first term, the number 1, and then add the second term, the x, and then add the third term, the x squared? No? What should I start with? I should start by adding together the 299th term and the 300th term, okay? That's what I should begin with. Those are the biggest contributors. All of these terms are positive. There's no negatives, right? So I might as well start with the biggest ones. And then after I add those biggest ones together, I should start adding the next biggest one. So maybe after 299 and 300, I should try 298 and 301 and 297 and 302 and 296 and 303. Do you see what I'm saying? Add the largest ones first that are contributing the most, and you can get to your desired accuracy while still keeping the fewest terms. If you start like that, you may only have to add together 50 terms. But if you started from the first term, now you're going to have to add together 350. You know what I mean? Because you're spending all of your flops adding together very small numbers when the end result was going to be a really big number. So that's what I mean by that third bullet point. Do y'all have any questions about this? I can tell y'all are starting to get tired, especially after having Calculus 3 and then jumping into numerical back to back. It's a lot for one day. It is a lot. Okay, the following table shows two different Python implementations of the left Riemann sum, so the same one you learned back in Calculus 1. For evaluating the given integral for a rectangle width, h is equal to b minus a divided by n. So a and b are your lower and upper bounds of your integral. N is the number of rectangles we're going to use in our Riemann sum, so h has to be their width. Which code will require fewer flops?
First one.
Why the first one? Why would the first one have fewer flops? It has fewer lines of code.
Yeah, that's what I
Sage?
Second one has the multiplication outside of the for loop, and the first one has the s plus h within that for k range for loop. So I think that would make more flops in the first one because the for loop's iterating through it more times versus the second one that's only doing it once it's outside.
Mm-hmm. Yep, Sage is exactly correct. And the one on the left, every single time we add to the sum the area of the rectangle, the width of the rectangle times the height of the rectangle, and we add that to the sum. On the one on the right, it's a little bit unconventional. But what I'm summing up is not exactly the area of the rectangle because I haven't multiplied by the width yet. But the genius part is that if I was just going to multiply every single term in the sum by the same width, I could just wait until after I'm done looping through, and then it's one flop to multiply by the width of the rectangles, and not n flops like it is the first time. So it saves you n minus 1 flops, which is, maybe not a ton, but it's something. And that's what the goal was to see. Everybody gets it? Okay, you'll get the same answer. Both codes will run the same answer. And again, maybe a real life problem doesn't look exactly like this, but I'm just trying to get you into the mindset of looking for ways to be more efficient. So here it is. It's the same one that was on the right earlier. We're already doing the trick where we multiply by the width of the rectangles at the end. This time the question is, can you think of any way where you can reduce the flop requirement further?
Could you take the a plus h times k out of the for loop too?
Yeah. Yep, I think so. I'll have to think about this just a little bit, but you would need to start with something like a line before the for loop begins, where you set up x as being like a minus h, and then at the start of every loop, you could do that. Or maybe you could even, if we're being super picky about saving this, move that to the end of the loop. So that way, every time you're not multiplying h times k, you're just adding h. But you get the same result. Oh, sorry. And another thing I forgot. There we go. That's what I meant. You're just adding h to x. So x is increasing in value as we go. Yeah, that's what you do.